Okay, hi everyone, and welcome to this ASM webinar, Next Gen Image Analysis and Microscopy, Integrating Zero-Shot, Deep Learning, and Conventional Processing, sponsored by MIPAR Software. My name is Bob Brockler. I'm the webinar coordinator with ASM International. We are very, very happy to have all of you joining us today. If you have any technical difficulties today, dial the number that you see on your screen right now, 877-582-7011. This will connect you with a GoToWebinar technician. All of our participants are going to be in listen-only mode during the presentation, but we certainly do encourage you to submit questions at any time by using the questions window. Type your question in the box and just click the send button, and we will then receive it. And we're going to answer as many questions as we possibly can at the end of the presentation. For more than 100 years, ASM International has served the materials community by providing scientific, engineering, and technical information, as well as education, networking, and professional development. Advanced Materials and Processes is ASM's flagship technical magazine. The Tabby Award-winning magazine provides must-have information about leading-edge developments and trends in engineering materials. The magazine also covers emerging technologies such as nanotechnology, additive manufacturing, and management topics. Don't miss current metals and materials industry happenings with AM&P E-News, a bi-weekly e-newsletter. Subscribe for the premier and technical content online at asminternational.org. Our today's webinar sponsor is MIPAR Image Analysis. MIPAR is a world-leading algorithm development and image analysis software company. They specialize in efficiently, accurately, and reliably extracting measurements from complex images. From material and life sciences to aerospace and manufacturing solutions, MIPAR's extensive portfolio can assist in a variety of real-world applications. And ASM is very, very happy and proud to have MIPAR on board for today's webinar. You can find out more information on MIPAR in the handouts section of this webinar player. There's a brochure available for you to download for free right there. Our instructor today is John Sosa, the CEO and co-founder of MIPAR Software. John received his PhD in Materials Science and Engineering from The Ohio State University while focusing on characterization of titanium alloys. He continues to support automated image analysis solution development while driving business development and overseeing product innovation.
All right, thanks very much for attending, everyone. I'm going to go ahead and get started. So I did as Bob mentioned in the intro, I did my PhD in microstructure characterization, and we spun out MIPAR about 7 years ago. The focus has been on helping researchers and engineers deploy practical automated image analysis solutions to what we deem real-world problems. So today I'm going to talk about what we view as next-gen image analysis, specifically as it relates to microscopy and materials, and we're going to cover how we've integrated the latest in AI image analysis, which is zero-shot detection, what preceded it in terms of AI, known as deep learning, as well as conventional image processing, and how all three of those integrate together to really usher in this latest wave of image analysis functionality for automating complex problems. So I'll start here with a brief intro to the MIPAR organization for those that are unfamiliar. It began as a project at a materials department in a university, was and is continued to be developed by those that use it almost every day. We spun out in 2017, as I mentioned, and we spent the last 7 years growing into hundreds of companies and schools worldwide. We're very proud to work with clients, both large and small, and we really appreciate those who gave our permission to share our partnership and their logo on the screen today. Most of our clients work under pretty tight NDA, so we really appreciate those that gave permission to share. So a brief look at the agenda for today. I'll define what modern automation is and why we view it as important. Introduce our latest AI tech, which we call Spotlight, and highlight the role that it plays in that modern automation. And then I want to spend most of the time demonstrating what the latest in automated image analysis is able to achieve on real-world problems. I'll try to wrap it up with some takeaways and leave plenty of time for the question and answer session. So when it comes to the incentive for automation, I like to express it with this simple accuracy versus speed axis. Most manual solutions are trusted to be accurate, yet I think most recognize the low precision and high operator variability that they bring. But of course, despite often being trusted, at least on average, as a source of truth, they are extremely slow and tedious. So for routine applications, something like these perfectly etched, noise-free grain boundaries, which you rarely see in practice, what I call last-gen automation, which would be tools or solutions based solely on tools like simple thresholding, morphology operations, things have been around for 30 or 40 years in computer vision. While they're not necessarily always as trustworthy as manual analysis, their solution often comes close enough such that the dramatic acceleration that they bring is more than worth it. And when you look at modern automation's impact, while it can offer marginal improvements in speed and accuracy, it's usually not worth the upgrade from classical tools, and it certainly doesn't tip the scales in terms of automation adoption if the last-gen automation technologies didn't do it for you. But in reality, the majority of real-world applications are complex. Something like these heavily twinned, difficult to define grain boundaries, if you throw last-gen automation on it, it fails to accurately identify or recognize what are grain boundaries. It simply identifies any sharp edge, therefore selecting all of the twins within the grains, and therefore it has no chance at accurate grain size quantification in this example, and none of its speed gains and cost reduction can be realized with such poor accuracy. So this is where modern automation can really make an impact, capturing the best of both worlds, so to speak, when it comes to speed and accuracy, allowing for these real-world applications to be acceptably automated and thus adopted. So in addition to accuracy, we've most frequently come across these criteria from our customers as far as what they require from automated solutions. Not only does it need to accurately detect features of interest, that's sort of a given, but the solutions need to be flexible and adaptable to meet their custom requirements. Maybe there are other features in the grain microstructure, for example, that need to be ignored, or there is a non-rectangular area of interest that they need to be detected within. Maybe they want them classified into different tiers of size population. All of those details are generally, to many customers, just as important as the accurate feature detection. In addition, they want the solutions to be simple to deploy. So once the algorithm is buttoned up, as few clicks as possible to get your analysis out. And of course, they need to be able to be validated. So we need to have some methodology and experience in validating what the automated solutions produce. A simple eye test goes a long way as far as whether the features are accurately found, but there are more rigorous projects we can run, gauge studies, for example, between the manual results and the automated results in order to provide some numerical justification for why the automated results should be trusted. So as far as how we really see modern automation, here it is. A collection of tools and their integration, which allow computer systems to meet or exceed human performance in feature detection and measurement performance. In MIPAR, we've included technologies that run the spectrum of intelligence. Each have their own advantages, but it's really their integration which allows for the fully automated complex solutions that I'll cover today. The first is classical processing. So those would be your thresholding, morphology, filtering, feature separation tools that have, as I alluded to, been around for several decades now. Then you've got your deep learning capabilities, which allow for the training and running of convolutional neural net models for much more advanced feature detection and classification. And finally, the latest in AI comes in the form of these new transformer network models, these prompt-based models, much like ChatGPT and other large language models. And these allow for some highly generalized so-called zero-shot performance, where models which have been trained on massive data sets well outside of the microscopy space can recognize features that they've never seen before without any training on those specific features being necessary. And we'll get much more into this in just a bit. And as I said, it's really the integration of these three technologies that result in the most powerful of solutions. For example, being able to take the output of a deep learning model, use it to prompt the next gen Spotlight AI model, and then refine and optimize the result with a few classical processing tools to ensure features are properly separated, ignore artifacts, and so on. So when it comes to this latest tech, which I've mentioned, we leverage it into a functionality we call Spotlight. Now, as I hope you'll see, we view Spotlight as a groundbreaking generalized artificial intelligence software that enables systems to see objects of all kinds, very much like humans do, even and especially on those objects that it's never been seen, it's never been shown before, it's never seen before. Now, the most important part, beyond just the technology itself, is how it's been integrated into the rest of our platform. So it's been integrated in two ways. The first is as an automated recipe step. Recipes in MIPAR are what we call the algorithms, the sequence of image processing steps, which tells the software how to select the features you're looking for. Most recipes now are heavily dependent on a deep learning and a Spotlight step, as well then as some other classical steps for cleanup. So this first form of Spotlight integration is as a recipe step that can be added in the image processor application. And this step is called Spotlight itself. So as an example, here is a grain structure we'd like to segment. We can simply open the image for the first time in the image processor, and then open the Spotlight recipe step tool and use its default grid mode, where in this case, each green dot is going to prompt Spotlight to look for a feature beneath it. So with the default settings, it's going to analyze the image, run through all of those prompts, and report back with the segmentation outlining the features that it found. And we've seen this Spotlight step be a core component of a solution that works remarkably well and is very robust across a number of different applications, from particles to other grain structures, to defects, to layers, to inclusions, secondary phases. It has a general object awareness that has really taken computer vision to the next level. The second way that it's been integrated is in an intelligent drawing tool, which we call Snap. So there are still plenty of use cases where training a deep learning model, a slightly different architecture, a convolutional neural net versus the transformer network that Spotlight uses, but there are still plenty of places where custom trained deep learning models on your own features can result in a more efficient and more customized solution, especially when classification is required. So a tool like Snap can be incredibly valuable at speeding up and resulting in precise labeling or tracings of features, which are required, of course, in order to train deep learning models. So this Snap drawing tool is available anywhere you have manual edit tools, like in the manual edit step, which can be added to a recipe, or in the session processor application, which is where deep learning models are traced and trained. So here we see it working. In point mode, you simply hover over objects and it recognizes them, click to select. And in box mode, click and drag around your feature, release to select. So as I mentioned, this is quite useful for dramatically speeding up and improving the precision of the feature tracings, which go into training your own AI models. So we're going to look at 3 application areas today. Grains of several varieties, which are a great use case for the most basic use of Spotlight, which is that grid prompt you saw a slide before. Several cases of particle analysis, which are best solved with a more targeted Spotlight approach. I'll get into this in just a bit. And then a few applications which I hope will highlight the power of combining convolutional neural net-based deep learning models with a tool like Spotlight. So we're going to start with grains. We'll go back through the execution of the Spotlight step on this one example. As I mentioned, Spotlight is based on a transformer network similar to ChatGPT and other large language models, and is thus prompt-based. So effectively, when you hand Spotlight an image, the first thing it does is basically recognize every conceivable feature that it might possibly need to segment in the image. Then you take that processing and you prompt it either with a point or a box or a collection of points, and based on your prompt, it returns back a segmented feature from its initial interpretation. So much of image analysis now with tools like this is almost a form of prompt engineering, which I know we're getting a lot more familiar with the nature of using these modern language-based AI tools. So again, it's going to look at each of these green dots and try to identify the features beneath them without ever having seen this particular image before. There are a few settings, of course, that can be adjusted. The density of the grid points, some other score filters to adjust the confidence in the features that it returns. But with a single step here, we have 99% of the challenging part of image analysis done for us. Then with some additional processing steps that I alluded to, you can complete the boundary separation and remove artifacts, leading to an optimum segmentation. Now that's just one grain structure. And while it was easy to segment, the real value comes in the robustness that a Spotlight-based solution provides. So it's the closest thing that we've seen to a universal grain size analysis solution, or the basis of one, a so-called foundational grain size algorithm. So here's an entirely different microstructure and imaging condition, and the exact same recipe, the exact same algorithm with the same settings works quite well. And we can look at a variety of different microstructures with different appearances, different sample prep conditions, different underlying materials, and the exact same solution, even in the case of a more challenging instance like poorly defined grain boundaries or incompletely defined grain boundaries with some light twinning going on, it's still recognizing grains as humans do. Or even on cases like melt pools, which often are quite challenging to automate the recognition of with complexity and noise within and low contrast. Again, the exact same solution is working well for us here. Even on life science applications, such as muscle fiber analysis, where apparently their cross-sections look close enough to grains that the same solution does a really nice job at automated segmentation. So with a solution that's this robust, with little, if any, adjustment needed case to case, microstructure to microstructure, imaging setup to imaging setup, now we can routinely help users deploy a batch processing workflow with built-in reporting, which is exactly what a robust solution like this enables. So whether you're processing multiple images from the same sample or across various different cases like shown here, a single solution can now be deployed at once in an unattended manner where you hand it your images in our batch processor interface. You hand it the recipe to process, and you configure any report that you'd like to come out automatically. Out will come a batch report containing all the measurements, segmentation overlays, and side-by-sides that you've built into the recipe. So in addition to statistics like mean and max grain size in this example, of course, full grain segmentation allows for distribution reporting and visualization, where here each grain is color-coded by size, and that color map is matched on the histogram with an optional curve fit. And I think we all recognize that the quality of microstructural measurements, the quality of automated characterization is, of course, only as good as the quality of the feature detection. And that's why MIPAR places such an emphasis on allowing accurate and customizable feature detection, because the quality of measurements are highly dependent on that. It doesn't matter what standards or metrics your software claims to be able to follow or provide. If it doesn't accurately see the features, all of those measurements and standards are useless. So there's a heavy emphasis on detection, and then that detection permits a wealth of different measurements, which can be built right in to the same workflow. So moving on to particles now. I know I mentioned this is going to showcase a more targeted spotlight approach, but this one, in fact, doesn't even require that level of adjustment. We can throw a simple grid prompt at it once again, and it's going to run through and just immediately select the particles. Then a couple of classic steps can remove small false positives and ensure that clusters of particles are properly separated, giving us our final segmentation. Even down at the atomic resolution, where you're needing to employ a texture-based segmentation, there's no real mean intensity differences between these two regions. Throw the grid at it, and it will come back with a segmentation for you. Now, in some other cases, like these particle examples here, we can target Spotlight more specifically to improve performance and efficiency further. Before you saw simple grid prompting for a look everywhere kind of approach. Here we will combine some classical processing with our grid and say only put down grid points where in the lighter parts of the image, which is where I know particles have a chance of being. Ignore the darker regions, which can prevent some dark pockets from being falsely detected, and of course greatly reduce the number of prompts that need to be processed, resulting in a much faster solution. So here the exact same algorithm results in a quality segmentation for two very different particle morphologies, leading then to a single solution that can work on a variety of particle cases. So with the particles identified, the recipe can then perform size distribution analysis. Again, here the particles are colored by size with the distributions plotted and stats reported. And as mentioned earlier, shape distributions can be extracted as well. Things like eccentricity on the left, which is somewhat of a normalized aspect ratio. 0 in this case would represent a perfect circle and 1 a straight line. And on the right-hand side, roughness, which is sort of a measure of perimeter concavity and complexity. So think of a starfish as an example of a very rough object with a object that represents a perfect circle as having very low roughness. And we see that plotted here and visualized. So I'll conclude now with a few different applications that I feel really showcase the power of combining deep learning models with Spotlight. I'll start here with a particle cleanliness application, which requires not only particle detection, but classification. So Spotlight can, of course, easily find all the particles with nice, precise boundaries. But now for classification, to stay in the AI space, we need to hopefully rapidly train our own deep learning model to perform the classification. So for that, we can use a tool like Snap to very quickly and again precisely label a few features. Whoops. Go back here and run this. Apologies. I'll play it this way. So we can use Snap to come in here and allow rapid selection of various of the features in the different classes using this box mode, where we can select features across as many classes as we'd like to train. Again, this permits not only a lot of speed, but precise boundary outlines, which result in high quality models. So once the annotations are made, then we can train the model. And when you apply it to the rest of the image, this is the result that we get. So we certainly don't have the boundary precision necessary to accurately measure, say, the size of the particles in the different classes, but that's fine because we already have the boundaries precisely defined with Spotlight. So by combining these two results, we can end up with precisely outlined and classified particles, which can now permit size and shape measurements, for example, across the classes. Another way to integrate the two is to use the output of a deep learning model as a Spotlight prompt. So here in this example, we're not actually looking at grain size. We're looking at a layer thickness problem where the layer is defined by the ultra refined band of grains near the surface. So similarly, with a Snap tool, we can annotate cases of this and then produce a deep learning model that, when applied, produces this result. This we call a probability map, where the brighter the pixels, the more likely the model thinks the layer exists. So we can then select the largest, brightest area in a result like this, hand it over to Spotlight, use a box prompt to then result in a precise segmentation of that refined layer. Once you have that, of course, then you can produce a measurement like continuous layer thickness, visualized on a color scale with a corresponding distribution. Finally, we'll look at a weld dimensional analysis problem. We're seeing a lot more of this out in the space. The need to automate either simple or complex critical dimensional analysis from weld cross sections, whether they're weld beads or weld joints. We're seeing this demand increase quite rapidly. And this really serves as a nice case study for how we recommend most users develop their own recipes if that's a route they wish to go down. Our team develops recipes included with the software for our customers, but the users also have access to the same tools our team does. There's no scripting or coding required. They create these algorithms, these recipes, directly in the visual software environment. And this type of approach that I'll show now is a pretty nice general workflow for developing automated solutions of all kinds. So the goal here is to automate the detection and then measurement of these different weld bead cross sections. This is just a sample of the data. There are many more images, but these few represent a decent spread in the variation that the solution needs to accommodate. There's There's certainly nothing in common that a threshold could pick up on. In one case, the bead is darker than everything else. In another, it's lighter than everything else. And in a third, it's somewhere in between. So the approach here is to, again, use a tool like Snap to take some of these cases. I'll keep one aside for testing. And let's see if the video plays here. Where you come in point mode, you just click 3 times and annotate your classes, bead, background, and substrate. We can then repeat that with another example here, bead, background, and substrate. Or imagine these are any sets of features that you're developing a solution for. This then produces, again, when applied, this model produces probability maps like so, where they're certainly not good enough for accurate segmentation of the bead all on their own. I think this model was trained in 5 minutes, so we don't have the precision necessary to, again, precisely outline the weld bead for quality measurement, but they are perfect as a prompt into Spotlight, where again, the large bright region can be selected and its bounding box then used as a Spotlight prompt to effectively snap the edges of the map highlights to the features and give us high quality segmentation. Now, of course, all of this gets packaged into a single recipe, which runs the deep learning model, prompts it into Spotlight, cleans up any false positives with a size filter if necessary, and now you have a fully automated algorithm that you can run in a few seconds on your various weld beads. We can add in things like separating it at the substrate surface such that we can get a depth profile above and below the surface. We can measure various depths across the horizontal and get ourselves a variation in depths as well as an average. There's all sorts of things we can do integrated right into the same recipe once we have accurate feature awareness of the bead as well as its background and substrate. So again, we view the state of the art in automated image analysis to come from the intersection of these 3 technologies. And our goal has been to offer a platform that makes this integration accessible, especially for complex problems. A good rule of thumb, we like to say in our software, if you can see a feature with your eye, however you recognize it, there's a very good chance that we can configure the software to automate its analysis. We've seen users quickly develop and deploy robust solutions across a variety of application spaces, and instead be able to spend their time drawing conclusions from data and running more experimental cycles, which humans are arguably best at, rather than making tedious manual measurements like has historically been necessary for many real-world problems. So we encourage you to give the software a try. We have evaluations available. As Bob mentioned, please visit our site at MIPAR.us to learn much more. And now I'd like to, again, thank Bob for organizing and ASM for partnering with us on this, and thank you all for giving us your time and giving me your attention today. So I think we can open it up for questions now. And again, thank you all for your attention.
Great. Thank you so much, John. Sorry that I had a little technical glitch on my end, but that got resolved pretty quickly. Thanks to the attendees who were able to fill me in as to what was going on. So our speaker today again is John Sosa. He's the CEO and co-founder of MIPAR Software, and we will start taking your questions. And John, I should have mentioned this to you earlier. If at any point during the Q&A, if you want to refer back to your slides, just let me know, and I'll make you the presenter again.
Okay,
So
that sounds good. Thank you.
Let's dig in with our first question then. Does MIPAR accept images from any microscope?
That's a very good question. So the answer is yes. It is a post-acquisition analysis environment. So it simply opens digital image files that have been saved off of your microscope with its acquisition software. So as long as it's a digital image of pixels, MIPAR can open and analyze it. Out of the box, we support all of the basic formats, JPEG, TIFF, PNG, BMP, and then if a more exotic format is opened, often microscope manufacturer specific formats, you'll be prompted to download a library, and then the software will restart, and you then have access to, I think it's 150 additional file formats. So SEM, optical, X-ray, drone camera, iPhone, DSLR, it doesn't matter. We're agnostic to imaging instrument.
Okay, we have one more kind of a broad question, then we'll dig into some real specifics. This question is, what hardware is required to run Spotlight?
Another good question. So Spotlight can run on CPUs. On the Windows system, it can run on a CPU. We now natively support Apple Silicon Macs for Spotlight, which takes advantage of their system on a chip architecture where they put the CPU and GPU on the same die and allow shared memory. So that is minimum system requirement, of course, is to run on a CPU, but we strongly recommend, especially with Spotlight, to run it on a system if you're on Windows with an NVIDIA graphics card. It's still most performant on Windows systems with NVIDIA cards. We have a table in our user manual which can recommend various cards across performance classes. My workstation that I frequently run it off is a Windows 11 workstation, I think with 64 gigs of RAM and a modern Intel CPU with a NVIDIA RTX 4080 card, which runs about $1,000 and has 16 gigabytes of built-in RAM on the video card. So we're not talking a supercomputer or high performance cluster being necessary. A reasonably powerful workstation with an NVIDIA card is optimal for Spotlight. And then on the Mac, it can run again on Apple Silicon systems as they come. Generally, it's 2 to 3 times slower running on a Mac than it is on a Windows system with an NVIDIA card.
Okay, digging into some more specific questions then, and this first one came in about 15 minutes into your presentation. The question is, for the Spotlight segmentation, is there headless / API access? In other words, can it be run programmatically by an external script?
Very good question. So we do have a couple of APIs available in MIPAR that allow recipes to be run with a single line of code in your own applications. So we have one form of the API that comes as a Python library. So you can import the library and then run a Python method to execute a recipe and receive back raw segmentation and measurement results in a Python dictionary. We then also have a RESTful API that gets deployed as a Docker container that you can query with a REST call and receive segmentation and measurements back in a JSON format. At the moment, we are working on upgrading the API to allow it to execute Spotlight steps, so be able to run a Spotlight-based recipe. That is currently in progress. So officially at this moment, the API cannot run recipes which contain Spotlight steps, but we're actively working on that and it should be available soon. Currently, the APIs can run recipes with any other steps, including deep learning models.
Okay, thanks, John. Our next question came about 20 minutes into your presentation. Would you be able to analyze macro grains and provide the M grain size number per ASTM E112 Table 3?
Yes. So again, the first part of that is going to depend on accurate grain segmentation. Once that is achieved in the recipe, we can then add ASTM E112 based measurements. So built in, there are intercept measurements which can be run, which produce a ASTM grain size number per that E112 standard. On top of that, we can also construct custom measurements directly in the software, which allow us to construct formulas with operators and built-in measurements, formulas around built-in measurements to add on something like the macro M number per the E112 standard.
Okay, our next question is kind of a two-parter, and I'm going to ask the second part first. How are you able to distinguish between gold and copper?
So if you're referring to the particle cleanliness application that I showed, where SNAP was used to select examples of each class, as is the case with deep learning models, we don't exactly, always know what elements of the features it's using to base its classification on. We simply tell it, here are examples of gold, here are examples of copper. You figure out what makes them unique, build that into your model, and then we can apply it to everything else. So, ask yourself, I suppose, what is it to your human brain that distinguishes copper from gold? Chances are those are the features the deep learning model is learning to build into its classification. I hope that answered the question.
Yeah, very good. Thank you. And the follow-up to that is, on what basis are the particles colored? Is it random?
Oh, very good question. So all of the feature, well, should say, cases where I just showed segmentation results, like that's slide here, I suppose. Maybe if I could resume sharing.
Sure. Let me just make you the organizer again, or the presenter, I mean.
Sure. Thank you. So let me. All right, we can see that. Okay.
Yes.
Thank you. So if I go back to this slide here, so in this example where I'm just showing segmentation results, these colors are randomly assigned. So this is just choosing random colors to indicate what are separate objects. It helps visualize, for instance, that this particle is seen separate from this one, is seen separate from this one. In other examples where measurements were presented, like this next slide here, it's the same color map, it's the same color space, but now the features are color-coded on the basis of their size. So blue in this example would be very small particles down here in the 0 to 10 micron size range. Yellow would be up in the 50 to 60. So any place where you see colored particles accompanied by histograms, those are colored on the basis of size, or in this next example, shape.
Great. Thanks, John. And I think we'll just leave your slides up for a while because I suspect you're going to want to refer to your slide deck again.
Sure.
Next question is, for the welds analysis, could you explain more regarding steps where you get very bright or dark contrast? Do you use pixel contrast, or how to characterize the edges of the weld? There's a lot here. Can you do the similar analysis on weld crack size measurements, or a different algorithm would have to be developed?
Yeah, really good questions there. Let me just take a moment here and kind of digest the scope of the question. So for weld analysis, you're asking, can we explain more about these steps where we get the very bright dark contrast. Do you use pixel contrast, or how do you characterize the edges of the weld? Right. So again, we're really relying on the object boundary, basically the supercharged, if you will, edge detection capabilities of the spotlight model. So if I can go back to this slide here where we look at the different weld segmentations. So when we use the snap tool, which is powered by that same model, to basically objectively detect the edges. So as I said, it's been trained on millions of different objects of all types, not just materials, but natural scene imagery, you name it. And from that, it's understood what defines an edge for an object in an image. It's not always the same thing, right? Sometimes it's a boundary between two colors. Sometimes it's a boundary between grayscale intensities. Sometimes it's a boundary between different textures. If you recognize, say, the boundary of a house on a background of, its yard from a drone image, there are lots of things that are telling a human mind what defines the boundary of that object. So we've used Snap and its boundary recognition abilities to objectively select what the weld beads are and labels areas of the other classes. That's produced these models, which then get fed back into the automated Spotlight tool to select the boundary edges now in an automated fashion in an algorithm that can be applied automatically to other weld beads. So again, we don't necessarily know precisely what features it has learned that define these boundaries. I'm guessing in this case, it's recognizing this transition between a uniform dark area and a more textured area. This case, it's probably picking more up on the intensity differences. And in this case, you've got, something there. There's a few different things I think going on, but there are certainly something there telling you there's a boundary, and it's learning what those characteristics, or it's in the Spotlight's case, it's using its learned characteristics of general object detection in order to find those boundaries. I think there was maybe a bit more to the question. So can you do similar analysis on weld crack size measurements? Yes. So again, if it's a feature that you can see in an image that your brain recognizes as a feature with boundaries, then we can almost certainly teach or build a recipe, i.e. configure the software to automatically see and measure it. So yes, weld cracks either within the bead or at the substrate interface or along a joint boundary if you're not using a spot weld. We can configure the software to detect those cracks and then configure the measurements that fall out from that, whether you're looking just at a crack length or you want the average crack thickness along its spine, or a whole host of other measurements you might want to derive from the crack. We would construct a recipe or train you to construct one, and that can typically be done in minutes to hours.
Okay, thanks, John. The next question is a bit of a fragment, but I think what they're asking is, can this process be applied to 3D images?
Okay, very good question. So we do have a 3D extension to the MIPAR software, which allows recipes to be applied sequentially to the series of slices that then get stacked up to reconstruct your 3D microstructure. So it's primarily used for taking serial section data sets that have been captured either from a dual beam FibSem instrument, where you have an ion beam that slices off layers of material, and an electron beam that then snaps a picture after each slice, sort of like a micro deli slicer with a camera on it. And then you take all of those slices and you need to align the features to themselves. You need to segment the features out from each slice, and then you need to stack everything back up and create your 3D microstructure reconstruction. That is all supported by our 3D toolbox. that allows those serial section data sets to be processed in that manner. So most of the application of segmentation in a 3D workflow like that is done at the slice level by, again, creating a recipe and then applying it sequentially to all slices. That said, after that workflow is done, there are direct 3D space manipulations that can be done in our 3D toolbox to maybe three-dimensionally ensure features are separated from one another, clean up boundaries, reject false negatives or false positives, things like that. So the Spotlight algorithm itself would still run on a per slice basis, and that's how we would deploy it in the three-dimensional space. We're still first and foremost a 2D analysis platform. I'll say, to be upfront, maybe 5 to 10% of our users are in the 3D space.
Great. Thank you, John. So just a bit of a time check here. We have about 10 minutes left, and I think there's at least 15 questions left in the queue. Chances are we won't get to all of them, but John, I am going to send you a spreadsheet with all the questions in them, and perhaps you can respond to some of them following the webinar. Our next question is, we often have images that are not as good quality as your examples. How does your software handle imperfections like metallographic scratches or etching variations?
Sure, really good question. So, I did try to find images that weren't always the best of cases. We typically deal with the hardest problems, I'll just say, to be upfront. We're 7 years out now as a company, so there've been plenty of other tools that have been around for longer, and many of them open source. So it tends to be when we see a lot of cases where those other tools have failed to produce automated solutions due to artifacts like you mentioned, or extreme variation between cases. Those tend to be a lot of the applications that we see. So the software certainly has the ability to handle real world cases like that, where you don't have perfect images. So scratches can be ignored either by detecting them with a trained model and overlooking them, or training your model to basically see through them. If you have scratches in your grain structure and you're using a deep learning based approach, you can make your annotations in such a way that the software learns to overlook those scratches or other defects. So there's no one magic bullet that lets us ignore any image complexities. But again, that integration of those three technologies allows the software to be configurable enough and flexible enough to learn to handle those challenges.
Okay, our next question, how long does it take to train a deep learning Spotlight model?
Okay, really good question there. Let me first make sure that there's clarity between those two different technologies. So Spotlight requires no training. It is a built-in AI model that is general enough to recognize features without needing to be trained any further on your images. Deep learning is the other form of AI that the software employs that does require a model be trained on your features. And like I show here on this slide, this is where the two can work together. So this is the result of a deep learning model that you've trained on cases like this, and then you take its hotspots, so to speak, these bright areas that it sees, and you use them as prompts into the pre-trained Spotlight model to get nice, clean segmentations. So Spotlight produces this final segmentation. This requires no training. Deep learning model that would produce this. In this example, I think it took maybe 30 minutes to train this model on 20 or so different examples, but that time is very much variable on size of the images, number of images, and your computing hardware. So we see training times range from anywhere to 5 minutes up to 12, even 24 hours for the really massive data sets with maybe several layers of annotation. So it's quite variable, but in those high time cases, of course, much of that can happen, after hours overnight.
Okay, thanks, John. We have two questions from the same individual, and I think we'll try and take them together as they are definitely related. Are you open for personal presentation to evaluate my system and to determine the benefits and to adapt it? And let me scroll down and find part two of that. Would you be able to teach the system to differentiate cracks over solidification within the weld?
Yes. So I think I mentioned at least once that, customization is pretty much our default when it comes to working with customers. A custom recipe is included with new licenses that a customer acquires. So we almost expect to work closely with customers to configure the software for doing exactly what they need it to do. Sometimes that configuration is almost instant because there are recipe templates that ship with the software, but we can all, since during evaluation, customers want to see the software working on their own images. Aside from those built-in templates, our team almost always works to build a custom recipe for your or fine-tune one that we already have for your applications. So that configuration, like I said, can be almost instant if it's a case where the software has been configured for that many times before. If it's much more nuanced and unique, maybe that configuration takes a few more days, but that is sort of the standard method of operation that our team works with our customers to configure the software for exactly what we needed to do. So if by your question you asked, are we able to do a personalized configuration and present and then deliver that to your team for use in the software, the answer is certainly yes. That's what we do most of, quite honestly.
Okay, we're coming down to our couple last minutes here, but we'll try and get a few more in. Can we measure a intermetallic layer in PCBs?
So we do tons of layer detection and thickness measurements. I'm saying the answer is 99% chance yes. We would just want to look at the specifics of your image to give you an absolute concrete answer. If you can see the layer in the image, if there's something that tells you here's the layer, then almost certainly yes, we can automate its detection and measurement.
Okay, let's see. Are you aware of any applications in the pharma or medical development space who have been able to validate methods for particulate analysis with particulate identification?
Yes, so we didn't cover this product at all today because it is much more pharmaceutical and biomedical facing, but we launched an edition of MIPAR maybe 9 months or so ago now called MIPAR Checkpoint, which is just a recipe running environment wrapped in a number of compliance features like user access control and electronic signature and audit trail production that are required in the most of the pharma space in order to conduct automated analysis. So we have a few customers of that product which are using MIPAR Checkpoint to conduct automated particle classification and counting analysis in a environment that is, in the case of their US status, 21 CFR Part 11. One of the FDA regulations around the handling of electronic records. So we do have a few pharmaceutical customers in that exact space.
Thank you, John. We are unfortunately at the top of the hour. I think we could probably have done at least another half an hour with the questions that we still have remaining. So thank you so much, John Souza, CEO and co-founder of MIPAR Software. As I said, we don't have the time to answer every question that we received, but in a few days, all of our participants will receive an email with further contact information. And I certainly encourage you to follow up with our speaker for more information on this topic. Once again, I'd like to acknowledge the sponsor of today's webinar, MIPAR Image Analysis Software. More information can be found at mipar.us. Also, be sure to grab the downloadable brochure that's in the handouts section of this webinar player. I encourage all of you to complete the brief survey that will appear on the screen as you exit the webinar. With your input, we can continue to provide webinars with high quality, practical information that you can use. Thank you once again to MIPAR and John. Thanks to all of our attendees for participating in this ASM webinar, and I hope everybody has a great day.